the first time I ever do a podcast, but I'm looking very forward to this.
I mean, I can go on talking about greatness about photo and electrochemistry.
So wherever you look into, chemistry is really the solution.
And in coming years, you will see more photocatalysis being used.
I think it's a new one. Okay, I think the most important thing has nothing to do with the chemistry itself.
Hello, everyone. My name is Javed Iqbal. I'm hosting a podcast on molecular makers of Simplify. The purpose of this podcast is to basically engage some experts in the area of chemistry and talk to them about contemporary chemistry and how it's going to be useful for industry. Today, we have an eminent speaker, Professor Oliver Reiser, who's a professor at University of Regensburg in Germany, an eminent professor globally known for his work in organic synthesis, total synthesis, and lately in the last one decade or so, he's been working in the area of photocatalysis. Now, may I request Oliver Reiser, professor, to just briefly give a brief introduction about yourself so that we can take it forward.
Yes, thank you. Thank you very much, Javed. So I'm very excited to be here and part of this. It's the first time I ever do a podcast, but I'm looking very forward to this exchange. So my name is Oliver Reiser. I studied chemistry at the University of Hamburg. And while I was at Hamburg at this time, I had the chance to go to two other universities. I was at the University of Jerusalem and I was at University of California, Los Angeles, UCLA, doing short research stays in NMR spectroscopy, in calculation, computational chemistry. Then I returned to Hamburg, finished my PhD. After this, I did a postdoc, 2.5 years. The first postdoc was in industry at IBM Research Center at San Jose, California. And the second one was at Harvard University with David Evans, where I was mainly involved in stereoselective synthesis. I returned to Germany. I started my independent career at the University of Göttingen under the mentorship of Professor Armin de Meire. And from there, I had the first appointment at the university in Stuttgart back in 1996 as an associate professor. And then I was appointed as a professor of organic chemistry in 1997 at the University of Regensburg. And I have been there now since more than 25 years. It's a very engaging environment for doing research, a very good university, and also a beautiful city. So I can highly recommend if you ever have the chance to visit here, don't miss it. We are a UNESCO World Heritage Site. It's really a very beautiful place and a good place for science. And especially with respect to also India, I have a research group of about, in the moment, 20 PhD, master, and postdoctoral students. And I have a very significant number of students from India. I have 6 PhD students in the moment from India. And it has been, this kind of collaboration has been going on for a long time. And it has been wonderful for me. I very much always enjoy the co-workers from your country.
Thanks, Oliver. You know, Professor Oliver Reiser is globally known today for his work in photocatalysis. Photocatalysis is an area which is emerging and it has a profound impact in industry. And in coming years, you will see more photocatalysis being used because it comes under the whole area of green chemistry. And Professor Reiser's group has been really a pioneer globally in this area. You know, he has a very big group. I have been involved. I mean, I visited him once for the month and also shared a course with him. In fact, Professor Reiser and I have a common PhD students that we produced, and he was a wonderful host, and I really appreciate and like his chemistry. You know, Simplify actually is now heading towards adopting some of these enabling technologies in photo and in electrochemistry, which is the future of industry in terms of making molecules. in a more greener fashion. And of course, Professor Reiser's group has been sort of involved in a lot of very new technologies and new methodologies that could really make their way into the industrial processes at a later date. So Simplify is also actually is looking into some of these areas, and currently Simplify has adopted a kind of catalysis, and we have made certain molecules in this area, and currently our R&D is heading towards that. And all of you will be very happy to know that Professor Oliver Reiser is going to come on our scientific advisory board. He's accepted it. So we will really benefit from his presence in Simplify with his new catalysis and the new way in which we can make molecules. So with this now, I think I'll switch over. I can go on talking about greatness about photo and electrochemistry, which is the future, but I think we have limited time. So I would now jump into Professor Reiser. The very first question I would like you to answer. Professor Reiser, you have trained and worked across very different research cultures. What was the key inflection point that shaped how you chose problems? May I hear from you, please?
Yes. So I think to answer that question, this will not have anything to do with electrochemistry or photochemistry. I always wanted to make a contribution to pressing problems of society. And I know it's a very small contribution as a single person with a research group of enthusiastic students. But if you look at today's challenges, you can take whatever you want. It can be environment, it can be sustainability, it can be drugs, it can be health, it's organic, inorganic, it really doesn't matter. Chemistry will always have to be the answer to a lot of these challenges. And from my point of view, having chosen the profession of chemistry, I really feel one can make an impact in just about any area. And so for me, I have always chosen problems where I felt that I can make a small contribution to pressing problems. And so for me, being an organic chemist, sustainability is a key factor. Renewable resources will become of a major importance if we think about that. If we want to replace oil for renewable resources, we have to change the way we're doing chemistry entirely. Everything we did in the last 150 years, we need to embark on new methods in order to be able to not use fossil fuels, which are hydrocarbons, of course, but using renewables, which are sugars and related compounds. And so this is something which I feel in the moment is a very huge problem where I would like to contribute. I see one of the challenges I see very much, which concerns me a lot, is the poverty in the world, especially when it comes to food, being able to feed the world. Again, a major contribution of chemistry. Without chemistry, without the Haber-Bosch process, we could only feed half of our population today. So wherever you look into, chemistry is really the solution, and not as it is often taken in the public, it's not the problem. And so for me, having chosen this profession in general has been very rewarding, because I feel that it makes sense for not only for myself, but also for the greater good of society.
Great, brilliant. Now I'm going to ask Professor, the students who are entering in these enabling technologies today, what is the biggest misunderstanding they have about so-called hot fields like photocatalysis and electrosynthesis? Can you give some ideas on that?
Yes, I think the biggest mistake you can make is that you think that one technology will solve everything. And I'm old enough now that I have seen emerging asymmetric catalysis. I have seen the resurrection and the development of organocatalysis. Then we have seen combinatorial chemistry, flow chemistry. A lot of enabling technologies have come around. And I think it's a big mistake if you think that if you limit yourself to one of these technologies, that this will change the world or the way of chemistry. I think indeed you cannot do everything. As an organic chemist, you try to be as broad and as round as possible. but you need to focus, if you're working on research and development, you need to focus on some technologies. And so for us, during the last 10 years, it has been especially photocatalysis, which I think is a very important tool in order to develop and do transformations, which also have a lot of challenges. So that's not that we can say photochemistry, it's actually a technology which has been developed already very much in the 70s and 80s of the last century. But it's one technology which we focus in the moment, but we are really open to all the other technologies as well. We're doing transition metal catalysis in my group. We're doing organocatalysis. We do peptide structure. So we are trying to be really, really broad. And of course, when it comes to catalysis, I see also, and not just photocatalysis or electrocatalysis, I see again from a point of sustainability, I see some pressing needs. And one of the needs is that we are using precious metals in catalysis. And it doesn't matter if it's transition metal catalysis or photocatalysis. If you look at this, most of that chemistry is iridium, ruthenium, platinum, palladium, very scarce and very expensive metals. And so that's one of the things which I feel very strongly about, not just from the point of photocatalysis, but also from any type of catalysis, that we would like to develop chemistry with earth-abundant metals. Think about this. If you can do catalysis with iron instead of palladium, this would change entirely the way resources would be available. And so that's, again, something we look into this, and it is indeed photocatalysis and electrocatalysis, but I always try to keep an open mind and always encourage my group to be as open and always look for the best way to solve a problem and not just getting stuck into one technology.
Great. Very, very, very nicely put. Very, very nicely put. So in continuation of that, Professor, photochemistry and electrochemistry existed for decades. No. Why did they become powerful now? What changed in catalysis or in catalyst hardware or in mindset? Can you give some thoughts on it?
I think it's a number of things. So if we look at what I would like to call the resurrection of photocatalysis, this really started around 2008, and with some very beautiful work from many eminent groups. And I think most importantly here is to name the group of David Macmillan, who got the Nobel Prize already for organocatalysis, and I dare to predict that there might be another one around the corner. But I think one of the really breakthroughs, and again, I'm old enough, I did photocatalysis in my PhD work, and that was medium pressure mercury lamps. You could not leave them overnight alone. You had to spend the night in the lab because you would be afraid that the cooling would go off and then everything overheats and explodes. Right. And so this alone, the technology we have now, LEDs, which are allowing you to irradiate a compounds at a given wavelength at very, very low cost. And that is, I think, one of the keys. This technology based on the LEDs has become available to just about anyone. You can, for really a few euros and probably a few hundred rupees, you can build yourself, you can get started in photocatalysis. And I think that's one of the really strong points, is that it really comes down to having great ideas. It's not coming down any longer to being able to do this from a monetary basis because you might not be able to afford it. And so I think this is something we witness. We witness from all over the world. We have witnessed so fantastic developments in photocatalysis, for example. And India has been at the forefront. People like Ganesh Pandey have done in the 80s and 90s groundbreaking things with organophotocatalysts, which now people have done with metal-based catalysts. And it's really fantastic. And so I think it is, by and large, besides some great ideas and concepts, but photocatalysis became available to just about anyone for almost no money. I mean, in the best case, you could run this in a normal flash in the sunlight, right? And that makes that I think has been the game changer in this field.
No, actually, Professor, you made a very important point. It is the metal catalysis versus electrocatalysis, and metal obviously is having its own baggage in terms of green chemistry and all. I'm going to ask you a very profound question now. In retrosynthesis terms, what does thinking in electrons and photons add that the classical disconnections have missed?
I'm not sure if the classical disconnections have missed it. If you think about photocatalysis, there are the two big areas: photoredox, where a photocatalyst will accept or give away an electron to a substrate, or energy transfer. And both of these technologies have been around, and also with the photoredox catalysis, you typically enter the field of radical chemistry, and of, again, fantastic contributions to radical chemistry in the 70s and 80s. Dennis Curran, Bernd Giese, and many more people have really contributed to this in a major way. I think the photocatalysis, especially also with the metal catalysis engaged, allows you to run a lot of these reactions, as it says, catalytically. So it's not stoichiometric generation of radicals any longer. And it allows you to simply do, as you already pointed out, things maybe in a greener way, although you almost need to be careful with the greenness of photocatalysis, because the light is expensive, because that's in the end electricity, and that might be actually a hurdle to adopt it on large scale. The one thing I feel to be very intrigued, or one of the concepts you can do with photocatalysis, is that you can drive an endothermic reaction. So a reaction where the starting material is of lower energy than your product. This is something you cannot do in a thermal regime, because the equilibrium will be on your lower lying starting material. Now with photocatalysis, you can lift your starting material to an excited state. So the light energy brings it up to an excited state. And from there, you go to a product, and there it is downhill. That your product now has higher energy than your starting material. But because you go from the excited state, you go and you bring you lift your molecule to a higher energy state. And then if that molecule of your product cannot absorb light any longer, it cannot go back. And I think this is something we might see a lot more, that we can drive, and these might be disconnections then to think about this, because normally we always think about chemical reactions that they need to have a driving force. And the driving force typically is you go from a starting material, which has a higher energy level, to a product which has a lower energy level. And if you're, and very often you might have to do then, if you want to lift it up with chemical means, you need to use reagents like butyllithium or so to make the highly reactive intermediates. And this is something you can do by light. And this gives you something, this was not really coined by me, this term, but this allows you to do what I would call uphill catalysis, that you go from lower energy to higher energy. Something nature is doing in a fantastic way, right? That's converting CO2 into sugar. So nature knows this for a long time. And for me, this is one of the most exciting areas which photocatalysis can offer.
I think your analogy is beautiful, very, very nicely. So now I'm going to ask another question that actually often people say. Photoredox is radical chemistry, made easy. What is the deeper truth behind that, and what is the dangerous oversimplification?
So again, I think for a number of reasons, for a number of reactions, this is true. These type of reactions could have been done in a thermal regime where you would generate radicals. Typical radical initiators have been tributyl tin hydride a lot. That is ecologically not very good in combination with a radical starter. But in principle, you could have done the same transformation. And again, I need to mention people like Dennis Curran, Bernd Giese, who really showed this in a and many more. I'm unfair here. Showed this in a beautiful way. I think photocatalysis can offer more, can offer new concepts also within the regime of radical chemistry. So, for example, the ability that a photocatalyst can take and give an electron to a substrate in any given time simply might change the way the intermediates are generated.
Yeah.
You can adjust in what we call now dual photocatalysis, where you do photocatalysis with a photocatalyst in presence of another metal catalyst. You can adjust by the photocatalyst the oxidation state of the of your transition metal catalyst. So this again opens up completely new ways to either make a process catalytic, which was not catalytic before, because your transition metal catalyst would not go back to the correct oxidation state. And it might also make transition metal oxidation states accessible. We're working a lot with copper. So copper 3, very difficult to deal with in a thermal regime, becomes accessible in order to do chemistry. Many more concepts. The concept of radical sorting, now again very much pushed by David McMillan, I think allows you in a spectacular way to do radical couplings. It's one of the things we always say, two radicals will not couple with each other because both of them are very low in concentration. They will never find each other. And so again, this is changing because one radical might get stabilized by a transition metal catalyst because it coordinates to this. And then the second radical comes in and is doing the coupling. So I totally agree. Radical chemistry has been around, fantastic contributions. But I think with a photoredox catalysis, the spectrum has broadened a lot.
You know, one of the very important things you mentioned about copper-3, existence of copper-3, which is normally not very, it's almost impossible to produce. And I think under these conditions, you're doing so. So I think it's a remarkable achievement. So let's put now something more important. Now, suppose you had a target transformation, let's say. How do you decide between whether you want to have photoredox transformation and how do you kind of decide between photoredox, electrochemistry, and classical metal catalysis? What is your mental decision tree, as we call it? Between the three, of course.
Yeah, between the three. So I think the one thing to make the big distinction is between working in academia, where you typically do smaller scale, so maybe gram scale, but not beyond, or if you would be working in industry where you need to do scale up to kilogram or even ton scale. And I think admittedly one has to say photochemistry can be scaled up. There are industrial processes who have used photochemistry on really large scale, but the scale up is an issue typically solved by flow chemistry. But it is an issue you would like to, probably from an industrial point of view, you would like to substitute. And for example, this is something we will start now doing more and more in our group. We have developed over the last 10 years a number of photoredox-based processes, but we haven't really asked the question if we can do the very same thing by electrochemistry. So we will revisit the reactions we have already done and which we know under redox conditions. We will see if that same thing can be done under electrochemistry. And then I think if I would then make the distinction between the two techniques, if I can do both techniques for the same reaction, probably the electrochemistry will win because it will be more scalable. And also if you think about quantum yields, many photoreactions have very low quantum yields. So the electricity cost is much less favorable in a photoreaction than in an electrochemical reaction. As I already mentioned, for me, one of the really things I would like to push as good as I can is replacing precious metal catalysts for earth abundant metal catalysts. And if you think about what we're doing in the moment in photocatalysis, a lot of the beautiful chemistry that has been developed is based on iridium. Now, iridium is one of the scarcest metals we have on Earth. Yeah. It's 10 times more scarce than palladium. It's 10 times more scarce than gold. And so it is, I think, although if you look at this from an industrial perspective, industry is very good in recycling precious metal catalysts. But still, I believe that if we could change this, if we could go to 3D metals, and we like copper and iron, fantastic chemistry has been developed with cobalt and nickel, manganese, titanium. I think it is there. It is just more challenging. We also know why this is not working so easily, because excited state lifetimes, you see, if you bring a photocatalyst into its excited state, it needs to live long enough to give an electron or its energy to a substrate. And that is the problem. The 3D metals, excited state lifetimes are nanoseconds at best, maybe picoseconds. That's too short. Iridium, ruthenium is microseconds. So that is 1,000 times better, at least. And so this is why it works so well with iridium and ruthenium. But I think we should not stop there. We need to look for more sustainable alternatives. And we are trying to do this in my group. Other people are also trying this very successfully. And so I think, again, if you ask me which of the three factors is important, for me always, if I do metal catalysis, no matter if it's photo or thermal, but for me it's always cost of catalyst is really important. And also, obviously, earth abundant metals have tremendous advantages. But think about this. How many catalytic processes do you know with iron? We do iron for reduction of nitrobenzene to aniline, but that's stoichiometric. That's heavily stoichiometric. We do Haber-Bosch with iron type catalyst. That's heavily stoichiometric. There is really not so much. And every student in a textbook, if you ask them and say, give me a palladium catalysis, give me some ruthenium catalysis, or everybody can answer this. But 3D metals is much more challenging. But on the other hand, it's good. So it will keep me busy, and it will keep future generations, will keep it busy.
So I think, Oliver, you mentioned a very important that D3 metals have to be really, looked into. And I remember when I was with Dr. Reddy's, we were looking into alternative to palladium, ruthenium, and platinum. And we did some work on iron, cobalt, and nickel, and that kind of thing. Now, moving on, now there's a question of reproducibility of reactions. For instance, what are the two reasons I want to know a photoredox reaction fails to translate across labs, even when the procedure looks identical?
Yeah. And I think what we do these days is we try to do a very good job by accompanying the papers which we write by very detailed supporting information where we describe the reactor, where we describe the light source, where we describe the intensity of that light source. We make photos of the reactors. And I think this is one of the big issues with photochemistry, is that a reaction which works in one reactor might not work in the next reactor. And it might be that, and again, you need to be sometimes very careful. You might have an LED and the LED says 3 watts, but that LED might have been in operation already for, let's say, for 100 or 150 experiments. And so if you do now measure again the output it can give you, it might only be 1 watt any longer. And so there, I think this is the moment where you need to take a lot of precautions and just be very much aware that you might not reproduce something which is described in a paper, although in your mind you do. The one advice, especially maybe to PhD students or so, I can give you is, if you run into such an issue, don't be shy to write to the group who has reported this. And typically they will go out of their way, because everybody does not like to get an email saying, I tried to do your reaction and it's not working, right? So people will go out of their way to help you, accommodate you, find out what you might do differently and what they might have done in order to get this in hand. And There are very nice publications from my colleague Burkhard König here at the University of Regensburg, where they took the same reaction and they have run it in 5 different photoreactors, and they got 5 different yields. And so again, this is the one thing which is very, very important. And I believe that by describing the experimental details as accurately as possible, this will help. And I'm still convinced that many reactions you might have tried in your lab, also a PhD student might have tried in the lab, that they did not work because the chemistry did not work, but maybe you didn't have enough light intensity. We see this now a lot. I mean, in the beginning, we had LEDs, maybe 1 watt. Now I'm reading papers which have 20 watts, 30 watts, 300 watts. It's just amazing. I almost, to the point that it becomes dangerous. And a lot of these things need to simply be taken into account. And for example, this issue on light intensity, we have been revisiting reactions we couldn't do 10 years ago, and now we have a more intensive light source, and now suddenly it works. So yeah, I guess these are the problems you run into.
Since you mentioned about students a short while ago, now what is the advice if a PhD student wants to become excellent in this area? What should they master first? And what kind of collaboration should they actively seek?
Okay, I think the most important thing has nothing to do with the chemistry itself. I think you need to be enthusiastic. You need to like what you do, because only the things you like, you will do well. Think about this of a career as a scientist. We probably studying included, we're talking about 40 years. And if you go to the lab and every day hate it, it will not work well for you. And so I think that is something I cannot treasure high enough. And we had, especially in Germany, we had for a long time, we had the job perspective from chemical industry was fantastic. It was clear that if you had studied chemistry, you will land a high paying job. But if you only started studying chemistry because you were hoping to have a good job afterwards, this did not really work out well so much. And so that's the one thing I always take. Also, when students apply to my group, if they are enthusiastic and I get the feeling they like what they are doing, this is for me more important than maybe that they have had a lot of courses already and bring a lot of knowledge with this. And in that respect, I would again like to especially commend the Indian students. I mean, they are so enthusiastic when it comes to chemistry. I have my students here in the lab who just enjoy that maybe my infrastructure might be a little bit better than they had it at home. And they're so happy that they suddenly can run reactions, they can buy chemicals, and they can do it. And it always pays out because the enthusiasm is really key.
Absolutely.
And then of course you think about what you would like to work in, and that can also change. I mean, for me, it was organic chemistry. I think when I started out chemistry, I wanted to become an inorganic chemist. In between, I liked mathematics a lot, computational chemistry. You need to find the area you like, and I think any area in chemistry will make meaningful contributions. And again, this is the one question you want to ask yourself: do I want to do the science for the purpose of science, or do I hope to contribute to challenges we see in society? And if you answer that yes, then of course I would not do certain types of research, and find something else where I have the enthusiasm, because I hope will be able to contribute.
Right. Now, this is a personal question to you. Now, looking back, what was one decision, maybe topic, method, collaboration, that compounded over time and changed your trajectory from pure synthetic organic chemist who did a lot of work, to photocatalysis, electrocatalysis, and all that stuff?
I think again it was a technology which came out and it was suddenly everybody could do photocatalysis because the LEDs became so cheap, and I think that was of course a major driving force for me that we wanted to start in this. By the time I did a few photochemical experiments during my PhD, but nothing major. But then to get into the field, our first publication came out in 2011. To get into this field, all it was buying for less than 20 euros, buying some LEDs. Our machine shop stitched them together, and we could simply start. And so that probably got me into. And again, the overarching area for me is that we really like to work with renewable resources. And I saw opportunity also in photochemistry. We think that if you go from sugars, we think an ideal platform of furans, and from there that you can do with non-edible renewable resources. Again, a major political and societal issue is that if we all go to renewable resources, we are starting to compete with food production. The biggest process we do in the moment with renewable resources is bioethanol, but the bioethanol comes from corn, and we still have millions of people who are starving. And I understand that you cannot just redistribute resources very easily, but I think for someone who wants to develop chemistry with renewable resources, I can take that factor into account, that I want to start with renewable resources which are produced in parallel, but not in competition to food production. And so this over the years has changed for me a lot, because I think still for me, hunger in the world, I don't need to drive a big car or have fancy vacations or so. But if I have to go to bed hungry, if I do not have medical care, I think these are the major issues. And so for me, from a synthetic type of chemistry, where I acknowledge that we need to switch over more and more to renewable resources. So the one decision I made is that these should be renewable resources which do not compete with food.
Very well, very well put. I think, Oliver, splendid. I think this is a beautiful statement you made. Now, this is more of a fundamental question that basically I'm sure you must have been asked, but I'm going to ask you, if you were to summarize on one line, what is the real shift these methods bring to organic synthesis? Is it green chemistry, new selectivity, or new bond logic?
I think it's all of these, and it allows you to so if you think about bond logic, it allows you to generate intermediates, let's say radical anions, radical cations, which usually are very tough, which had to be in an environmentally unfriendly way in order to access them. So you can make reactive intermediates in a very green way, and these reactive intermediates allow you to make new bond connections. So I think it's very well put. The three aspects you did, I think they all connect with each other.
Great, very good. So what is one transformation class where photocatalysis is genuinely first choice today, and why? Why do you think this is the first choice?
The first choice. So as I said earlier, I'm very intrigued by this possibility to do uphill catalysis, to convert starting materials that are of low energy into products of high energy. And essentially what you do in this course is you store the solar energy or you store the light energy into the product. And this might allow you to do new types of chemistry. So for example, you have just developed a photochemical Lewis acid-based reaction from furans, which makes cyclopropanes. And it only needs light. It needs light and a Lewis acid. It's 100% atom economic, and it starts with furans. So we are really excited about this. And then if you think about the alternatives, typically the alternative to make a cyclopropane is that you use a diazo compound. So this is now your high energy component, but you need to make it, and that's not in an environmental good way. And so I think, again, photocatalysis allows me in a green way to make uphill, to develop uphill processes. And I think that is something which is where photocatalysis and also electrocatalysis by by the way, in the same way. So we're typically talking about radical anions, radical cations, which are produced in a very green way by just putting on electrons and energy, either from the electrode, if you think about electrochemistry, or from light and the photocatalyst to a molecule.
Great. So you have covered both. I remember your cyclopropionation on your furan. If you remember, one of your thing was I remember a long time ago. So
I think it's a new one. I think it's a brand new one. We have not even published it yet.
Sure, you're not.
Yeah. So I think what you remember is that we did furan cyclopropionation with diazoesters.
Oh,
but now we can make the cyclopropanes by not using a diazoester. We are making them by completely renewable resources from furan and an aldehyde. We are getting out the cyclopropane. There is no waste. It's 100% atom economic. And of course, we are going uphill because the cyclopropane is strained. But the way we drive it uphill, the reaction, is that we use light. And so the light energy gets stored in the end in the product. And that is, in our opinion, in the moment, this is as green as it can get. And so that's what we are really, really excited about.
One thing I think you've already covered in electrosynthesis and in photo. Now, there's one question always that sort of haunts everybody, organic synthetic chemist, is the reproducibility in electrosynthesis, and what are the hidden variables organic chemists often don't report or notice until it's too late?
Yeah, I'm not sure. So first of all, I think if you look at papers these days where you might have a 4-page paper and then you have 150 pages of supporting information, I think people go out of their way already to really document the experiments as carefully and as detailed as they can do. And of course, there are always still, in the end, if you can make a picture of your reactor, but it's a difference that if you're standing in front of the reactor and run the reaction, right? And so there are things which might be, one might be unaware. If you think about electrochemistry, the electrodes, the electrode material is very important, but sometimes you might have a graphite electrode. You think you have a graphite electrode, but if you were very carefully investigate it, maybe it is coated with something. Maybe it has been contaminated with something because you ran a reaction before. So this is something I believe also people are aware of, that this can be a complication. You try to document it, but this can be something that it's not intentionally, it's unintentionally that you are having a reaction set up where you also do not know all the parameters. And this has happened even in the same lab. I had reactions which we would run for 10 years and many generations of students did it, never had a problem. Suddenly coworkers come to me and say, the reaction is not working any longer. And I say, it's impossible. We are running this since 10, 15 years. And then, of course, you start chasing why that is. And that can be very often difficult, and especially difficult if you have run this for a long time and you're not aware that you changed anything.
So now, Oliver, I'm going to ask you a very important question from the standpoint of industry. As you know, industry always looks into scaling up large volume production, manufacturing, and all that stuff. Now, if you were to really use the photoelectrochemistry-based technologies, now, what are the key constraints you think when moving from, let's say, as these people have used clever in a while to useful at scale for photo and electrochemistry?
Yeah.
I mean, scaling up basically is a major thing because industry would always eventually look into these technologies,
of course,
whether they can make these on ton scale or kilo scale and those kind of things.
Yeah.
What are your thoughts on that?
Yeah, so absolutely. And I think typically the photochemistry also, as it is done in industry, is a very, very important tool when it comes to screening, when you want to get large libraries or sort of compounds, and you just need a few milligrams or even a few grams. But if you go to scale up, the problem, of course, is in a larger scale, the light penetration of your light source into a reactor is only a few millimeters. So if you go from a 10 milliliter vial to a 2 liter flask already, the efficiency is not so good. This is why we do flow chemistry. And again, I might point out that flow chemistry in combination with photochemistry is inexpensive to set up even for a academic lab, because we take tubing, Teflon tubing, and we wrap it around a light source. So there's really no limitation for an academic lab that they cannot try things in flow. Still, at that point, we are probably still talking about a few grams, but we are not talking about more. My understanding in industry is that if you have a reaction, or a target molecule, which has been produced by a photochemical way, and they need it, they will try to find another method. One has to be as clear as this, and only if there's really no alternative, they will go for the photo reaction, because it's a scale up, but it's also the cost of electricity. If you have a photochemistry reaction which has maybe a quantum yield of 1% or so, you put in a lot of light energy, that's electricity, into your compound. The one thing I see if I go from photoredox to electrochemistry is that this might be very related. And that's what I said earlier. We are looking at photoredox processes. The photoredox catalyst gives or takes an electron, but the electrode can do the same thing. And so to set up a photoreaction, at least because everybody has LEDs also around, might be the easier way. But then to revisit the same process by electrochemistry, that is a very logical way. And I would predict, and I would say we have seen it for some of our reactions, it works most of the time. And then at that point, the scalability, it's a completely different picture. And so there you will be able to scale this up.
But Professor Reiser, what about flow chemistry? Can we not adopt flow chemistry to this
yes.
photo?
Yes, of course. Absolutely, and of course this is done so you can do the reactions in flow very easily, and so then probably the biggest drawback might be the cost of electricity. So yes, flow is I think is a technique not only to scale up photoreactions, but I think flow is in general teaching us how to scale up reaction without that you need to construct a big reactor, and so. I think absolutely the flow technology is something to.
I have seen some publications or some work in industry using flow chemistry, using photo or even electrochemistry.
Yes, absolutely.
Interesting emerging area for industry to adopt, and I think flow chemistry could be a good way of scaling up of a kilo or multi-ton scale.
Yeah. But again, it's a ton scale. I'm aware of processes. I think Merck is making one pharmaceutical drug by a photochemical step, and I think there we're talking about 100 kilograms or so. But if you go to a company like BASF, where they make things on really a multi-ton scale, then I'm not sure. I might be completely wrong on this, how well this will go with flow chemistry, but I think that the hurdle compared to a batch reactor, which can have a volume of maybe 10,000 liters or more, that is still a pretty big transition.
No, I think if you talk about, I agree completely with you talking about few kilos, and there are therapeutic areas and their APIs require only kilos.
Yeah.
And you could, like for instance, in oncology drugs, you don't require tons. There are those kind of APIs could be quite amenable to flow chemistry using photo or electrochemistry.
Yes. And since we and again, if you think about this, and I think this is also something we will see more and more. Again, fantastic work which has been done there already. it might come to the question, can I do the photo, and that same is true for the electrochemistry, but can I do the photochemistry without the photocatalyst? Because is it maybe just that that you need to choose your reagents in a way that they can form these light absorbing donor acceptor complexes, and then you're not relying on a catalyst any longer. And we see more and more processes which, and you always need to do the control anyhow, which work sometimes not quite as good, but they work very well without the photocatalyst. And I think if we start understanding this better, or have maybe not the classical metal photoredox catalyst, but maybe having some additive which allows you to generate the light absorbing species in a different way. I think this will help, because with the flow chemistry, of course, then you also need to pump through the catalyst and everything.
Correct.
So the best reactions, the one I mentioned earlier with the furane to make cyclopropanes, we are not even using a photocatalyst. It just works by itself.
I just want to take a little away. I mean, digress from for half a minute. This mechanochemistry is also becoming very important nowadays.
Yes.
What is your view on mechanochemistry?
Yes.
Can you combine it with photochemistry?
I'm not sure that I could do it, but I think I have seen papers who did this, right? And again, it comes a little bit. You need an apparatus in order to do this. You need these ball mills, and it's funny enough that in some labs also from even old time, they had these ball mills for different purposes, and they can use it now. And so, yes, so we have not looked so much into this because we simply do not have an apparatus, but I'm very impressed what I see in the literature, what people are developing in this. So that again comes, and it's not only that it saves you the solvent, right? But it saves you, it enables chemistry which would not be possible in a solvent. And I think that's again, it's a fantastic development. You see, we have seen so many of these techniques. We have seen microwave chemistry. And I think microwave chemistry again has had a major impact to run reactions faster, cleaner. A lot of techniques, and I view ball mill chemistry for this as well. And we probably should think about getting one, just to have. I like to have in my group as many techniques.
Very interesting. And another area which a friend of mine in Australia is working on is surface acoustic wave. I'm sure you've heard about it. I think it's fascinating. Maybe we can talk about some other day. Now, before I jump into rapid fire questions, the last question I have: over the next 5 years, what do you think will move from specialist techniques to default tool in synthesis labs, and what must happen for that shift? It's a fundamental question, a very philosophical question. What is your view on that?
I wonder if it will be anything which we are seeing right now. I think we are all seeing the big thing of artificial intelligence in the moment. And so maybe the artificial intelligence will suggest us reactions which we are completely unaware in the moment. I'm not really sure we are there yet. Everything I've seen so far from synthetic AI programs was not really, could not really compete with the human mind. But I think this is, I think we are in a constant process of seeing new technologies. I think, quite honestly, I think electrochemistry will become much more important because it combines the advantages of photochemistry, making reactive intermediate in a clean way by giving or taking electrons, and it will not have the scalability issues so much. So I think this will come. I think the combination of photo and electrochemistry will also come much more, right? This is already what's being done right now, that you generate electrochemically a photocatalyst, right? So the electrochemistry makes the photochemistry, then you irradiate this, you bring it back to the wrong oxidation state, and then the electrode helps you again to bring it back. I think we will see this a lot, and I dare to say that if you look in the moment how fast artificial intelligence is developing, that artificial development will play a major role in designing processes in a very sustainable and beneficial way.
Brilliant, brilliant. This is amazing. This is something, your last question. Now get ready for some, what they call it, rapid fire questions.
Okay.
Okay, and then I will let you go.
Okay.
Okay, so Professor, in the rapid fire, the first question I have is one concept you wish every synthetic chemist understood about controlling redox. Tough question, maybe.
No, you need to know redox potential and excited state lifetimes. These are the two major parameters, and of course the absorbance of your substrate or your photocatalysis. So the wavelengths, excited state lifetime, redox potential.
Okay, so what is the one most underappreciated parameter in photochemistry people don't appreciate? Quick.
I think it's the light intensity. It's yeah, because we are not making mistakes in the absorption and the redox potential. This is all measured, but you might irradiate and you think you have 3 watts and you have only 1.
And can you say the same thing about electrochemistry? Underappreciated fact about electrochemistry?
Yes, the electrode material. You might think you have a graphite electrode, but it might be contaminated also from a previous experiment. And you are running, and it can be both good or bad. It can be that it works, but it will only work with your electrode. Or it can be that a reaction should work and it's not working because you have a contamination problem or not the electrode material you think you have.
And one myth you want to kill in the field. What is the myth you would like to kill?
That one technology can solve everything. You need to have many of the technologies available. It's the benefit of being in an academic group. I can always add and start using new techniques. And I think this is, you should not be too stubborn that you think that your methodology is the only one which can solve the problem.
Yes. Okay, so what is the one go-to reaction class that you think will become mainstream? One reaction class.
It needs to be a conversion of renewable resources into fine chemicals. So, for example, think about this. If you could make from glucose, which is a C6 body with lots of hydroxyl group, if you could make cyclohexane out of this, you would be in the oil business, and you could use what we have developed for 150 years in the past. You could use the renewable resources. So I think this is something we need to see. If we want to use renewable resources, we have essentially to rebuild chemical processes which we have developed all over the years for 150 years based on oil platforms. And there are 2 ways to do this. You can start from a renewable resources and you tap into compounds you already know from the oil route. Or maybe we need completely new reactions. Maybe we will have new drugs because we cannot synthesize aspirin from glucose. But maybe we can make a drug which is as good as aspirin, and it comes from a sugar molecule.
So you're basically talking about deoxygenation of sugar.
For example, I think deoxygenation in a sustainable way is, and again, the energy, it costs energy because the carbon-oxygen bond is a strong bond in order to break this. But you need to develop such chemistry in a sustainable way, and ideally without waste. You can, in my point of view, you can use all the energy you need for this, because if we have,
it's also green, because during the deoxygenation process, you're only going to produce water, I guess, right? No carbon dioxide, no oxide.
Water or even oxygen, right? It would be good, but it needs to be it needs to be green for this, right? The same thing probably with chemical hydrogen production and things like this. We need to look for processes where the byproducts are not oxidized carbon, for example, where the byproduct is not carbon dioxide.
So now the last question is, which is very important for you personally, what is the best advice you received as a young scientist?
Stay curious and enthusiastic. I think this is the the best thing I like. I love it when students come to my door and say, can I talk about chemistry? I hate it when they come and say something in my of course it's important, don't get me wrong, but if they say on my paycheck there were 10 euros, not enough or so, right? So I think the enthusiasm you need to have for what you do, and especially since we are chemists, the enthusiasm and curiosity for chemistry, this is the biggest trait you can have. And as I say, I love to talk about chemical problems, and of course, you always like to discuss with students the project when it works, but I think it's equally important to figure out things which do not work. I love to look at NMR spectra, and I can do this for hours and discuss this with my coworkers. And I think this is the one advice I simply cannot overstress enough. Only what you like, you will do well.
Great. I think this has been a wonderful podcast. Other people who are listening to it would have really gained a lot of interesting ideas. Also, how photochemistry, electrochemistry has a future for industry. Professor Reiser's insight into many of those questions that may have been in the mind of many of young students, perhaps have dispelled a lot of those myths, because of course a lot of students still have those mindsets which basically think, oh, organic chemistry can only be done by mixing two things and heating. But I think you have really clarified a lot of myths about using photo and electrochemistry, the photons and electrons. And I think this is amazing podcast. You have really enriched a lot of people, and I think Simplify has been a sort of pioneer in getting these people. I mean, we have been doing this, and now we'll do more in terms of really making some newer ideas, new science, new technologies to the people. And I'm really delighted about this, and Simplify actually is looking forward to your wisdom and your guidance in coming years. And I think I just thank you for your time, and thanks everyone for listening to this podcast. Thank you very much.